You have seen them before. The pictures of other worlds. A strange ocean under a double sunset. Red cliffs beneath an alien sky. A blue planet, not unlike our own, hanging in the black. Hold one of those in your mind for a moment, and then consider a quiet, surprising fact. Every single one of them is a painting. We have never photographed another Earth. We have never truly seen one, not once. Every image you have ever been shown of a second home among the stars was imagined by an artist and painted in where the real thing has never come into view. We have found thousands of distant worlds, that part is true, and we will spend the night among them. But the home we keep looking for, the twin of our own, has so far stayed just out of sight, in the dark beyond the reach of every instrument we have. This is a story about that gap, so settle in and let the lights go low, and let us walk slowly out into the dark together while you drift off to sleep. If you sit an astronomer down someone who has given 30 years of their one life to this search, and you ask them a very simple question. Name one. Out of all those thousands found, and those millions believed to be waiting, name a single planet that you are confident could hold life. If you ask them that, they go quiet. They look away. They begin to qualify, and to hedge, and to explain, because the honest answer, the one that lives underneath every hopeful headline you have ever read, is that they cannot. Not one. Not with confidence. Not yet. This is not a story about finding a second Earth. It is a story about why, after all of this looking, we have not, and about what it might mean for us if we never do. So settle in. Let the lights go low. There is nothing here you need to solve tonight, and nothing you need to carry out of this room with you. This is just a long, slow, unhurried walk through everything we have found and everything we have not. Out there in the dark, a quiet accounting of the catalogue and the silence, told gently while you drift off to sleep. We will start, as these things always start, with hope. To understand how strange our situation has quietly become, we have to go back to a single telescope and to the simplest idea in all of planet hunting. In the year 2009, we launched a spacecraft whose only real task was to stare, not to travel anywhere in particular, not to chase a comet or to photograph a planet in the way you might be imagining. Simply to watch. To hold its gaze on one small patch of sky, a narrow window tucked between two constellations, no wider than your hand held up against the night, and to keep watching that same window without blinking, without drifting, for years on end. The telescope was named Kepler, after the man who first worked out the true shapes of the orbits 400 years ago by candlelight. Inside that small window sat roughly 150,000 stars, and Kepler watched all of them at once. Over and over, thousands upon thousands of times, it measured the brightness of every one of those stars, looking for the faintest imaginable change. A dimming so slight that no human eye could ever catch it. The idea behind this is so gentle that it almost sounds too simple to work. Imagine a single star as a distant streetlight, burning steadily at the far end of a long road. Now imagine a planet circling that streetlight, swinging around it in a slow and patient loop. Most of the time, that planet is off to one side, and the streetlight shines at its full and even brightness, unbothered. But every so often, if the angle between us is just right, the planet passes directly in front of the light, crossing the narrow space between the streetlight and your eye, and in that moment, it blocks the smallest sliver of the glow. The light dims, just barely, just for a few hours, and then the planet moves on along its orbit and the light comes back to full. That tiny, repeating dip is a shadow, It is the shadow of a world cast across the face of its star and out into the dark all the way to us. And from that shadow alone, we can learn a surprising amount. From how deep the dip is, we can judge how large the planet must be, because a larger world blocks more light. From how long the dimming lasts, and how regularly it returns every few days, or every few months, or once a year, we can map the planet's orbit and how close it rides to the warmth of its star. All of this without ever once seeing the planet itself. We never see the world. We see only the shadow it throws as it crosses the light again and again, keeping its quiet and faithful time. This is called the transit method, and for a few astonishing years, it remade our entire understanding of the sky, because Kepler found planets. It found them in numbers that nobody had quite braced themselves for. By the year 2015, it had confirmed more than 1,000 worlds, and it pointed toward thousands more, still waiting in the data to be checked and confirmed. There were small planets and enormous ones, worlds in scorching, hurried orbits that took only days to complete, and worlds drifting slowly through the cold, far from their suns. And out of all that abundance came a single lesson, which arrived slowly and then seemed suddenly obvious, and it was this: planets are not rare. Planets are not some lucky accident, some unlikely arrangement that our own star happened to fall into. Planets are ordinary. Planets are the rule. Very nearly every star you can lift your eyes to on a clear night holds a family of worlds of its own, circling it patiently in the dark, whether or not we will ever see them. It should have been the most hopeful discovery in the long history of this search, and in one way, it truly was. But folded carefully inside that hope was a second fact, much quieter and much colder than the first. And that second fact is where all of our trouble begins. Think back for a moment to that perfect crossing the planet, passing squarely in front of its star. For us to catch that shadow, the planet's whole orbit has to be lined up almost exactly edge-on, as seen from where we happen to sit. The flat plane of its orbit has to point toward us, so that the planet, on its way around, slips directly between its star and our waiting telescope. If that orbit is tilted, even slightly, then from our particular corner of the galaxy, the planet sails harmlessly above the star or below it and never crosses the light at all. It casts no shadow we can keep, and so we never know it is there. It is still a real world. It still turns and warms, and perhaps it even holds an ocean. We simply have no way, with this method, of ever finding out. And here is the cold arithmetic at the center of it. For a planet riding at a comfortable, temperate distance from a star much like our own, the chance that its orbit happens to be tilted edge-on toward us, the chance that we get to see it transit at all, is only around 1 in 200. 1 in 200. Which means that for every single planet Kepler managed to find, there were, on average, something close to 200 more. 200 worlds circling those very same stars turned just slightly the wrong way and so kept entirely hidden from us. Not too faint to see, not too distant, simply pointed in a direction that gives us nothing, made invisible by nothing more than the geometry of where we are standing and where they happen to be turned. And the stars themselves were far away. Most of the ones Kepler watched lay between 600 and 3,000 light-years from us, so distant that the light now arriving in our telescopes left those stars before the first stone cities of the ancient world were ever raised, and has been crossing the emptiness patiently the whole time since. So, sit with the shape of this for a moment, gently, because it is the seed of everything that follows tonight. The single telescope that proved, beyond any reasonable doubt, That planets fill the galaxy from end to end, that very same telescope also proved that we cannot see the great majority of them. The ones we can see are simply the ones that happen, by luck, to be aimed at us. And as we are about to find, again and again, the ones that happen to be aimed at us are almost never the ones we are most quietly hoping to find. You have, almost certainly, read the headline before. Some version of it floats up every year or two, and it always says very nearly the same thing. Astronomers discover Earth's twin, a second Earth, found at last. Earth 2.0, just next door, and each time, for a day or so, it feels as though the long search might finally be over. But each time, sitting quietly underneath the headline, there is a problem the headline did not mention. Not a lie, exactly. Just a hope, dressed up a little too quickly, and sent out into the world before anyone had quite finished checking it. So tonight, slowly, with no urgency at all, let us walk back through a few of these almost Earths, one at a time. And in each case, let us turn the world over gently in our hands and look at the thing the headline chose to leave out. We begin in the year 2011 with a world named Kepler 22b. It was the first planet Kepler turned up that sat squarely in what we call the habitable zone. That phrase will come back to haunt us before the night is through, but for now, hold the simple version of it. The habitable zone is the comfortable band of space around a star, not too close, not too far, where the warmth is gentle enough and steady enough that water on a surface might stay liquid rather than boiling away or freezing solid. Kepler 22b lay about 620 light-years from us, riding in that comfortable band, and the headlines reached, almost helplessly, for the obvious word, twin. But Kepler 22b is about 2.5 times the width of our own world. And at that size, it is very probably not a place with any ground to stand on at all. A world that large, gathered up out of the same cold materials, tends to hold on to a thick and swollen envelope of gas and ice, which means that beneath the clouds there may be no solid surface anywhere, only deeper and deeper layers of crushing air with no floor ever arriving. Or, if it is a world of water rather than gas, it may be an ocean with no end and no shore. A sea thousands of kilometers deep, wrapping the entire planet with no island, no coast, no patch of dry land breaking the surface anywhere upon it. We had stood up and celebrated finding a habitable world before we had truly settled what the word habitable was even going to mean. Then, in the year 2016, the search came suddenly and thrillingly close to home. A planet was found circling Proxima Centauri, and Proxima Centauri is the very nearest star to our own, only about 4.2 light-years away. By the vast standards of the galaxy, that is not across town, that is across the street. And this planet, which we call Proxima b, was small, close to the size of Earth, and sitting right in its star's habitable zone. For a little while it seemed almost too kind, too neat, that the nearest star of all should turn out to hold a candidate for a second home. But Proxima Centauri is a red dwarf, and we are going to spend real time with red dwarfs tonight, because they sit at the very center of our problem, so let us simply meet one here. A red dwarf is a small, dim, cool ember of a star, far smaller and far fainter than our own, burning slowly and stingily, giving off a deep red light. There are a great many of them, and for all their dimness, for all their slow and frugal burning, they have a temper. Proxima flares. Without warning, it erupts sudden, violent bursts of radiation, some of them many times more powerful than the very largest flares our own star has ever produced. In the year 2017, a single one of these flares brightened the little star 1,000-fold in a matter of seconds and then faded back. Now picture a small planet huddled in close to that star for warmth, century after century, for billions upon billions of years. If Proxima b ever held an atmosphere, an air of its own to breathe and to shelter under, then that star has very likely spent something like 4.5 billion years stripping it slowly away, flare by flare by flare. And so the nearest candidate we have for a second Earth may in truth be a bare and blasted stone, scoured down to the rock by the very star that is supposed to warm it. The very next year, in 2017, came what was perhaps the most beautiful find of all. A system we call TRAPPIST-1. 7 planets. All of them close to the size of our own world. All 7 circling a single small star, packed in tight and orderly, like a model of a solar system built at 1/5 scale. And 3 of those 7 sat within the habitable zone. As a piece of pure detection, it was breathtaking, an entire miniature system handed to us at once, near enough and neat enough to study in real detail. And yet, these 7 planets orbit so close to their small, cool star that they are almost certainly tidally locked. That is a phrase worth slowing down on. To be tidally locked is to keep one single face turned toward your star forever. Exactly the way our own moon keeps one single face turned always toward us, so that there is a near side we have always seen and a far side that, for most of human history, no one ever had. A tidally locked planet does the same thing to the star it circles. One hemisphere held in endless, unmoving day, the other lost in endless, unmoving night. On the day side, a heat that never eases. On the night side, a cold that never lifts. And along the dividing line between them, the slender ring of permanent twilight that wraps the planet from pole to pole, the temperature might just possibly be bearable. But the wind's there, tearing from the burning side toward the frozen one, trying forever to even out that impossible difference, may howl along faster than the speed of sound. 7 worlds the size of Earth, gathered around one little star, and not a single one of them a safe place to rest your hope. Closer to our own time, a world named K2-18b drew the gaze of the most powerful telescope we have ever built and flown. And here the idea grew stranger and more tempting than ever. K2-18b was put forward as something genuinely new, a world with a thick hydrogen sky laid down over a deep, planet-wide ocean of liquid water. A warm, dim, blue-gray world under a heavy atmosphere. And when the great James Webb Telescope studied the starlight filtering through that atmosphere, it found a faint trace of a molecule with a long name, dimethyl sulfide. On our own world, that particular molecule is made almost entirely by living things, by vast, drifting blooms of tiny creatures in the sea, breathing it out into the air. For one extraordinary moment, it looked as though we had caught the faint scent of biology rising from another world. But the signal was weak, so weak it could barely be told apart from the ordinary noise and flicker of the measurement itself. The very category of planet, that hydrogen over ocean world, was unproven and might turn out to be imaginary. And the world is more than 8 times the mass of Earth, heavy enough that, once again, it may have no surface and no ocean at all, only a vast and crushing depth of atmosphere pressing endlessly down. And so the most promising sign of life we have ever glimpsed anywhere may be drifting upward out of a planet that has no shore for it to have come from. And still, the procession does not end. In the year 2025, a 5th planet was carefully teased out of a system called L98-59, not by its shadow this time, but by the faint wobble it raised in its star, a heavier, rocky world, a so-called super-Earth, sitting in the habitable zone some 35 light-years off, circling yet another red dwarf and carrying with it all the same old burdens. The locked rotation, the flares, the long, slow erosion of any air it might have had. Then, more recently still, in the early months of the year 2026, a world named HD 137010b was announced, though only as a candidate, glimpsed in a single, faint crossing of its star, and still waiting on further observation to be confirmed. And for a single held breath, it looked like the closest match anyone had ever found. Only about 6% wider than our own world. And, rarest of all, circling a calm, steady, sun-like star, rather than one of the temperamental red dwarfs. The kind of pairing this search has been waiting whole decades to stumble upon. But the catch was hidden, as it always is, in the fine detail of the orbit. This planet rides along the far outer edge of its star's warm band, far enough out that its surface may sit below freezing always, locked under a permanent and unbroken winter. And so the nearest thing we have yet found to a second Earth may turn out, in the end, to be a world of ice. A twin, yes, but a twin wearing a shroud of frost. So here is where the first act quietly leaves us, with nothing yet resolved, and the night still young. 6,000 confirmed worlds, dozens of them sitting in habitable zones, headline after headline, year after year, promising a twin just over the horizon. And the conclusion, after 30 patient years of looking, is soft-spoken and a little brutal, both at once. We have found nothing that truly looks like home. Not yet. Every almost Earth has had its quiet flaw, its missing piece, its line of fine print, waiting underneath the hope. But there is a deeper and far more unsettling question waiting just beneath all of this, and we will turn toward it slowly as the night goes on. We have not yet found a true second Earth. That much is plain. The harder thing to sit with is whether we could even see one, whether we could recognize it at all if it were sitting out there right now, this very moment, in plain and ordinary view. So, let us ask the harder question directly. Here, in the quiet, suppose a true second Earth really is out there. A rocky world, the size of our own, riding at a gentle distance from a calm and ordinary star, with a thin blue sky and a wide ocean and dry land between the seas. Suppose it exists, right now, somewhere within reach of our telescopes. Could we find it? The uncomfortable answer is that, with the tools we have, we very probably could not. Not reliably. Not yet. And the reasons are worth walking through slowly, one by one, because each of them is a small lesson in how the universe keeps its quietest things hidden. Begin again with the transit, the shadow crossing that gave us Kepler's thousands. We have already seen that it only works when an orbit is tilted edge-on toward us. But for a true Earth, around a true sun, the problem runs deeper than the tilt alone. And here the idea grew stranger and more tempting than ever. K2, 18b, was put forward as something genuinely new, a world with a thick hydrogen sky laid down over a deep planet-wide ocean of liquid water. A warm, dim, blue-gray world under a heavy atmosphere. And when the great James Webb Telescope studied the starlight filtering through that atmosphere, it found a faint trace of a molecule with a long name, dimethyl sulfide. On our own world, that particular molecule is made almost entirely by living things, by vast, drifting blooms of tiny creatures in the sea, breathing it out into the air. For one extraordinary moment, It looked as though we had caught the faint scent of biology rising from another world. But the signal was weak, so weak it could barely be told apart from the ordinary noise and flicker of the measurement itself. The very category of planet, that hydrogen over ocean world, was unproven and might turn out to be imaginary. And the world is more than 8 times the mass of Earth, heavy enough that, once again, it may have no surface and no ocean at all, only a vast and crushing depth of atmosphere pressing endlessly down. And so the most promising sign of life we have ever glimpsed anywhere may be drifting upward out of a planet that has no shore for it to have come from. And still, the procession does not end. In the year 2025, a 5th planet was carefully teased out of a system called L98-59, not by its shadow this time, but by the faint wobble it raised in its star, a heavier, rocky world, a so-called super-Earth, sitting in the habitable zone some 35 light-years off, circling yet another red dwarf and carrying with it all the same old burdens. The locked rotation, the flares, the long, slow erosion of any air it might have had. Then, more recently still, in the early months of the year 2026, a world named HD 137010b was announced, though only as a candidate, glimpsed in a single, faint crossing of its star, and still waiting on further observation to be confirmed. And for a single held breath, it looked like the closest match anyone had ever found. Only about 6% wider than our own world. And, rarest of all, circling a calm, steady, sun-like star, rather than one of the temperamental red dwarfs. The kind of pairing this search has been waiting whole decades to stumble upon. But the catch was hidden, as it always is, in the fine detail of the orbit. This planet rides along the far outer edge of its star's warm band, far enough out that its surface may sit below freezing always, locked under a permanent and unbroken winter. And so the nearest thing we have yet found to a second Earth may turn out, in the end, to be a world of ice. A twin, yes, but a twin wearing a shroud of frost. So here is where the first act quietly leaves us, with nothing yet resolved, and the night still young. 6,000 confirmed worlds, dozens of them sitting in habitable zones, headline after headline, year after year, promising a twin just over the horizon. And the conclusion, after 30 patient years of looking, is soft-spoken and a little brutal, both at once. We have found nothing that truly looks like home. Not yet. Every almost Earth has had its quiet flaw, its missing piece, its line of fine print, waiting underneath the hope. But there is a deeper and far more unsettling question waiting just beneath all of this, and we will turn toward it slowly as the night goes on. We have not yet found a true second Earth. That much is plain. The harder thing to sit with is whether we could even see one, whether we could recognize it at all if it were sitting out there right now, this very moment, in plain and ordinary view. So, let us ask the harder question directly. Here, in the quiet, suppose a true second Earth really is out there. A rocky world, the size of our own, riding at a gentle distance from a calm and ordinary star, with a thin blue sky and a wide ocean and dry land between the seas. Suppose it exists, right now, somewhere within reach of our telescopes. Could we find it? The uncomfortable answer is that, with the tools we have, we very probably could not. Not reliably. Not yet. And the reasons are worth walking through slowly, one by one, because each of them is a small lesson in how the universe keeps its quietest things hidden. Begin again with the transit, the shadow crossing that gave us Kepler's thousands. We have already seen that it only works when an orbit is tilted edge-on toward us. But for a true Earth, around a true Sun, the problem runs deeper than the tilt alone. But to photograph a true Earth beside its star, from light years away, is like trying to photograph a single firefly hovering right next to the beam of a lighthouse and trying to do it from 1,000 kilometers off. The star is not merely brighter than the planet. It is something like 10 billion times brighter. The faint glow of the world is utterly lost in the glare, swallowed whole. We do have a clever trick for this, called a coronagraph, a kind of precisely shaped mask that blocks out the central light of the star so that we might glimpse whatever faint thing huddles nearby. But the masks are imperfect. Stray starlight always leaks and scatters around the edges, flooding back over exactly the place we are trying to see. The next great instrument built for this, aboard a telescope named for Nancy Grace Roman and expected to fly in the year 2027, should be able to take direct images of planets the size of Jupiter, enormous worlds, far out and well separated from their stars. A world the size of Earth, tucked in close to the warmth where it could hold an ocean, remains beyond its reach. So hold this in mind gently. The next time you see one of those beautiful paintings of an alien world, the swirling cloud tops, the twin suns setting over a strange and welcoming sea, remember that we have never once seen such a thing. We have never directly photographed a single Earth-sized planet in the habitable zone of a sun-like star. Not one. Every image you have ever seen of a second Earth is exactly that. A painting, a hope, rendered carefully by an artist, of a place no eye and no lens has ever truly looked upon. There is a temptation, when you hear that we have found 6,000 worlds, to imagine that we now hold something like a fair survey of the galaxy, a representative sample, a proper census, from which we might safely judge what is common out there and what is rare. It is worth setting that comforting idea down, slowly and for good, because our catalogue of planets is not a census. It is something much more misleading than that. It is a funhouse mirror, and it shows us mostly our own reflection. To see why, return one more time to our two great methods and ask what each of them prefers, what kinds of worlds each one finds easy, and what kinds it quietly passes over. The transit method, the shadow catcher, strongly favors certain planets over others. It favors large worlds, because a large world blocks more light and casts a deeper, easier shadow. It favors worlds in short, fast orbits, because a planet that circles its star every few days transits again and again, giving us many chances to catch it, while a planet on a long, slow, Earth-like year offers us only one faint crossing every 12 months. And it favors planets around small stars, because a given planet blocks a larger fraction of a small star's face than of a large one's. Add these preferences together, and you can already guess the shape of what comes back. The method finds, most easily, big planets, whipping around close to small stars on orbits of just a few days. And so that is what fills our catalogue. The wobble method has its own favorites, and they point the very same way. It feels most strongly the tug of massive planets and of planets in close orbits, because both pull harder on their stars. Once again, the big and the close shout loudest. The small and the distant, the Earth, stay quiet. So when you look at our great list of 6,000 worlds, and notice that it is crowded with strange swollen planets, scorching giants in 3-day orbits, hot worlds larger than Neptune, skimming low over their stars, it is easy to conclude that the galaxy simply prefers to make such things. But it does not, necessarily. We prefer to find them. Our catalogue is not a map of what exists out there. It is a map of what we are able to detect, and what we are able to detect turns out to be very nearly everything except the one specific thing we set out, all those years ago, to look for. And then there is a stranger pattern still, hidden in the numbers, which is not a trick of our methods at all, but seems to be something real about the worlds themselves. Astronomers call it the radius valley. When you gather up all the small planets we have found and sort them carefully by size, you might expect a smooth and gentle spread, some a little smaller, some a little larger, with no particular gaps. But that is not what we see. Instead, there is a curious thinning, a valley, at around 1 4/5 times the width of Earth. Above that size, there is a crowd of worlds, the so-called mini-Neptunes, wrapped in thick atmospheres of gas. Below it, another crowd, rocky super-Earths, dense and bare. But right in the gap between them, right around that 1 4/5 mark, the worlds grow strangely sparse, as though something were quietly removing them. And the most haunting part is where Earth sits in relation to this gap close to its lower edge, near the place where the population begins to thin. This is not merely a failure of our instruments. The gap appears to be genuine, and the leading explanation is a slow and patient violence. A world of just the wrong size, born with a modest atmosphere, sits close enough to its star that the star's radiation gradually boils that atmosphere away into space over hundreds of millions of years, stripping the world down, shrinking it across the valley from a soft mini-Neptune into a hard, bare rock. We do not yet fully understand why the line falls exactly where it does, but there it is, plainly, in the data. A hollow in the population of worlds, right about where the Earth-like ones ought to be standing. A quiet hole in the universe, and we cannot say for certain what is eating the planets out of it. And finally, we come back to the red dwarfs, because we cannot avoid them any longer, and because they hold the sharpest version of this whole problem. Remember what a red dwarf is. Small, dim, cool, and frugal. And remember too that they are by far the most common kind of star in the galaxy. Something like 3 out of every 4 stars that exist is a red dwarf. They are everywhere. And because they are small and dim, they are also, conveniently, the easiest stars to find planets around. A planet blocks a larger share of their modest light, so its transit shows up more clearly. A planet tugs their lighter bulk into a wider wobble, so its pull is easier to feel. For every reason our methods have, the red dwarfs are the path of least resistance, and so it is no surprise at all that the great majority of habitable zone planets we have found are circling these little red stars. But here is the quiet trap inside that fact. It is tempting to look at all those habitable zone worlds around red dwarfs and conclude that red dwarfs must be good places to look for life, that the galaxy is, helpfully, stocking its most common stars with its most promising planets. That conclusion does not follow. We find most habitable zone planets around red dwarfs for the same reason a person finds their dropped keys under the street lamp. Not because that is where the keys are most likely to be, but because that is the only place there is enough light to search. The red dwarfs are simply where our methods can see. The stars truly like our own. The steady, sun-like yellow stars of the kind that warms us now make up only about 7 in every 100. And finding a true Earth around one of those is the hardest task of all. It means watching far longer, on far more difficult targets, with far lower odds of success, while the easy red dwarfs sit nearby, offering up their crowds of locked and flaring worlds. We are searching for a second Earth, in other words, under the street lamp, because that is where the light happens to fall. And the place we most need to look, the place where a true twin of our world would most likely be found, remains out there in the dark, beyond the edge of the light, waiting and unsearched. We have used that phrase many times tonight, gently and without examining it, the habitable zone, the comfortable band, the place where water might stay liquid. It is time, now, in the deep middle of the night, to look squarely at that phrase, because it is one of the most quietly misleading ideas in all of this search. It is, in a sense, a kindness we have done ourselves, a way of making an impossible problem feel smaller and the great numbers feel a little less crushing. Here is the original idea, in its honest and modest form. It is sometimes called the Goldilocks zone, after the old story, not too hot, not too cold, but just right. You take a star and you ask a single question. At what range of distances from this star would the warmth be gentle enough and steady enough that water sitting on the surface of a world would neither boil away into vapor nor freeze solid into ice? Too close, and the heat is too fierce, and the oceans cook off. Too far, and the cold is too deep, and everything locks into permanent frost. But somewhere in between, there is a band, a ring of orbits at just the right distance where liquid water could, in principle, endure. That ring is the habitable zone, and that is the whole of it. One single variable, distance from the star. That is all the phrase has ever truly meant. But now, set that beside what genuine habitability, the real working capacity of a world to hold life, actually seems to require. It is not one variable, it is dozens, tangled together, each one able to ruin the others. A world needs an atmosphere, but not just any atmosphere. It needs the right composition, the right pressure, neither too thin to hold warmth, nor so thick it becomes a furnace, and it needs that air to circulate, to carry heat from the warm places to the cold ones. It needs, very likely, a magnetic field, an invisible shield wrapped around the whole planet, generated deep in a molten core, to turn aside the constant stream of particles its star breathes out, and to keep that stellar wind from slowly scouring the atmosphere away into space. It probably needs a tilt, a lean in its axis, to give it seasons, to share the warmth around over the course of a year rather than baking one band and freezing the rest. It seems to need plate tectonics, the slow grinding and recycling of its own crust, which on our world quietly regulates the climate over millions of years, drawing down carbon when things grow too warm and releasing it when they grow too cold, holding the whole system gently in balance. It may need a large moon like ours to steady the wobble of its axis, so that its seasons stay reliable across the ages rather than tumbling into chaos. It may need a great outer planet, a distant giant like Jupiter, riding the far edge of the system to absorb or fling away the worst of the wandering debris that would otherwise rain down. It needs an orbit that is close to circular, so that it does not swing wildly between scorching and freezing every year. And it needs a star that is the right type and the right age and quiet enough in its temper to leave all of this delicate machinery alone for the billions of years that life seems to need. Look at that long list, and then look again at the habitable zone with its single lonely variable. We took a problem with dozens of tangled requirements, and we quietly reduced it to mere distance. And then, when we found worlds that satisfied that one easy requirement, we allowed ourselves to call them habitable and to feel that the search was going well. It is an understandable thing to have done. It is also, when you see it plainly, a little bit like judging whether a house is a good home by measuring only the temperature of the air outside the front door. And we do not have to travel to distant stars to see how badly that single measure can mislead us. We need only look at our own two neighbors, the worlds on either side of us, both of which sit, by the simple definition, within our own sun's habitable zone. Consider Venus. It rides closer to the warmth than we do, at about 7/10 of our distance from the star, but it sits, by the generous reckoning, near the inner edge of the comfortable band. By the simple rule, it should be a candidate for life. And Venus is the closest thing to a vision of the underworld that exists anywhere near us. Its surface simmers at around 460 degrees, hot enough to melt lead, a temperature that does not change between day and night or pole to equator because the heat is so total and so trapped. The air presses down at the surface with something like 90 times the weight of our own atmosphere. The crushing pressure you would feel deep beneath an ocean, except it is the sky itself doing the crushing. High above, there are clouds, but they are clouds of sulfuric acid, and the rain that falls from them is acid too, though it boils away in the heat long before it can ever reach the ground. Venus sits in the habitable zone. Venus is a sealed furnace, and on the other side of us, consider Mars. It orbits further out, at about 1.5 times our distance, and it too falls, by the simple definition, within the habitable band. And Mars is a frozen and silent desert. Its average temperature hovers near 60 degrees below zero. Its air is thin, almost to nothing less than 1/100th of the pressure we live under, so thin that liquid water cannot survive on the open surface even where the temperature would allow it. It has no magnetic shield to speak of, having lost it long ago, and so the stellar wind has had its way with the planet for billions of years. There is water there still, but it is locked away as ice, in the poles and beneath the dust. Mars sits in the habitable zone. Mars is a cold and quiet tomb. So this is what our own solar system whispers to us, if we are willing to listen. We hold two worlds inside the sun's habitable zone, besides our own. One is a pressure-cooked hell, the other is a frozen waste. And only the single world wedged carefully between them, with its particular air and its spinning iron heart and its steadying moon and its slow-breathing crust, ever became a place where life could take hold. The habitable zone is not a promise. It is not even, really, a likelihood. It is barely a suggestion, a first faint hint of where to point the telescope, and nothing more. And now we must return, one last time, to the little red stars, because they are where most of our so-called habitable worlds are found, and because the truth about them ties the whole problem into a single hard knot. We have already met, in passing, the strangeness of life around a red dwarf. Let us sit with it now, fully, in 3 parts, slowly, the way you might turn a cold stone over in your hand. The first part is the locking. Because a red dwarf is small and cool, its habitable zone, the band where water could stay liquid, lies very close to the star. A planet warm enough for oceans has to huddle in tight, far nearer to its red sun than we are to ours. And at that range, the star's gravity does something quiet and permanent. It grips the planet's rotation and slows it over ages, until the spinning stops altogether, and the world is locked into place, one face turned forever toward the star, the other turned forever away. We met this already with the Trappist worlds, but feel the shape of it again. There is no sunrise on such a world. There is no sunset. There is no day giving way to night and back again. On one hemisphere, the red star hangs fixed in the sky, never moving, never setting, pouring down its heat without pause forever. On the other hemisphere, there is only darkness, unbroken, age upon age, and a cold that has never once been touched by light. The dayside scorches, the nightside freezes, and along the narrow seam between them, the ring of eternal twilight, the temperature might just allow for liquid water and a tolerable warmth. But that seam is also where the most violent weather on the planet must live, as the air rushes endlessly from the burning side toward the frozen one and back, trying and forever failing to settle the imbalance, raising winds that may tear at any atmosphere thin enough to be torn. We are placing our hopes, when we hope for life on these worlds, on a thin band of twilight strung between fire and ice, beneath skies racked by ceaseless storm. It is not impossible that life could find a footing there, but to call such a place Earth-like is an act of poetry, not of science. The second part is the flaring, and it is worse than the locking. Red dwarfs, for all that they burn slowly and will outlive every other kind of star, are restless and bad-tempered in their youth, and that youth lasts an extraordinarily long time. They flare sudden, brutal eruptions of light and radiation, some of them brightening the whole star by many times over in a matter of minutes, hurling out ultraviolet light and X-rays in violent bursts. Proxima Centauri, as we saw, can erupt so fiercely that for a few seconds it brightens 1,000-fold against its own dim glow, with flares far stronger than our own steady star ever produces. TRAPPIST-1 flares, without pattern or warning. Now place a planet in closer than any world in our own system rides to the sun, because that is where the warmth is, and hold it there while its star convulses, not once, but dozens of times a year, for billions of years. Imagine living beneath a sun that does not shine steadily, but instead detonates at random, each burst fierce enough to wipe out every satellite we have ever placed in orbit, fierce enough to reach down and strip away the upper layers of the air. That is the ordinary, everyday environment around the most common, habitable zone worlds in our entire catalogue. Not the rare, unlucky one, the typical one. And the third part is the slow consequence of the first two, and it may be the quietest tragedy of all. Follow the chain gently, one link at a time. Without a thick and stable atmosphere, there can be no liquid water held on the surface. Without surface water, there can be no carbon cycle, no slow breathing of the crust to steady the climate. Without that regulation, there is no protection from the climate swinging to ruinous extremes, and no shield held up against the star's ultraviolet glare. And without all of that, complex life on the surface has nowhere to begin and nothing to stand on. Each loss leads to the next. And the most recent and careful models suggest something heartbreaking, that many of these red dwarf worlds may lose their atmospheres entirely within the first billion years of their lives, scoured away by the relentless flaring while their star is at its most violent. Which means the air may be gone before life has had the time it needs to grow beyond the simplest single cells. The world may be sterilized before it can ever truly come alive. The most common habitable worlds in all our records, the crowd of little planets circling the galaxy's most numerous stars, may, in the end, be dead on arrival, warmed and watered for a while, and then quietly emptied, long before anyone could have been there to notice. So the habitable zone gives us a crowd of candidates. And when we look closely at that crowd, world by world, we find the same shadows falling across nearly every one of them. The locking, the flaring, the slow loss of air, and the rare, precious exception, a temperate world around a calm, sun-like star, is exactly the kind of world our instruments find hardest of all to see. The places easiest to reach are the places least likely to hold life. And the places most likely to hold life are the ones still hidden out in the dark. That is the trap. That is the shape of it. And it is, in its own quiet way, almost symmetrical enough to be beautiful. But suppose, despite all of this, that we do find one. Suppose a true and temperate world swims at last into view. And suppose we manage to study its air. Would we, even then, be able to tell whether anything lived there? That is the question the next act asks. And the answer, gently, is not nearly as simple as we once believed. Let us grant ourselves, for a while, an enormous and generous gift. Let us pretend that the detection problem has been solved. Imagine we have somehow found a true second Earth, a rocky, temperate world, the right size, riding at a gentle distance from a calm and ordinary star. We have it in our sights. Now comes the question that all of this has secretly been building toward. How would we know if it were alive? How would we tell from light years away whether anything at all breathed and grew and stirred upon its surface? And here, gently, we run into a second wall, quieter than the first, but in its own way, even harder to climb. We do have a method, and for a time it seemed like it might be enough. When a planet passes in front of its star, that same transit we have spoken of all night, a little of the starlight does not simply pass the planet by. A thin sliver of it shines through the planet's atmosphere on its way to us, grazing the very edge of the world, passing through its high air like sunlight through the rim of a soap bubble. And the gases in that air each drink up certain precise colors of light and let the rest pass through. So if we spread that filtered starlight out into its full spectrum of colors carefully enough, we can read which colors have gone missing, and from the missing colors, we can name the gases. We can learn, in principle, what the air of a distant world is made of, written into the light itself. This reading of the atmosphere through transmitted light is one of the most elegant things we know how to do. And the great telescope built to do it, the James Webb, launched at the very end of the year 2021, was meant to open this whole field wide. In one way, it has. For large worlds, for gas giants, and for the swollen mini-Neptunes, it has read their skies in wonderful detail, finding water and carbon dioxide and clouds and winds, world after world. But for a small, rocky planet, the size of our own, circling a star like our own, the signal grows desperately faint. Remember how little of a star's light an Earth blocks when it transits 8 parts in 100,000. Now ask, how much of that already tiny shadow is the thin rind of atmosphere alone, the part that actually filters the light? The answer is smaller. Still, the atmospheric signal of a true Earth is something like 1 or 2 parts in a million of the star's light, a small fraction of even that already tiny shadow. To pull a clear reading out of a whisper that faint, even the James Webb would need to watch dozens of separate transits gathered patiently over years under conditions close to perfect, with the star sitting unusually quiet the whole time. It is the most powerful telescope our species has ever built and flown. And for the one kind of world we most want to study, it is very nearly not powerful enough. But suppose even that were overcome. Suppose we gathered the transits and quieted the noise and read the air of a true Earth at last. What exactly would we be hoping to find written there? What gas would tell us plainly that something was alive? The usual answer, for a long time, was oxygen. On our own world, oxygen fills 1/5 of the air, and almost every molecule of it was breathed out by life, by plants, and by the tiny green things in the sea, splitting water and sunlight and giving off oxygen as the byproduct of their slow living. Left alone, without life constantly replenishing it, that oxygen would not last. It is a restless, reactive gas. It would bind itself to rocks and to other gases and quietly vanish from the air within a geological eye blink. So to find an atmosphere rich in oxygen, the reasoning went, is to find an atmosphere being continuously refilled, and what could be refilling it, if not life? Oxygen was to be the gold standard, the clearest signature, the breath of a living world. Except that, as we looked closer, we found that oxygen can be made without any life at all. There are several ways the universe knows how to do it. On a world growing too hot, with oceans beginning to boil, water vapor rises high into the atmosphere where the star's ultraviolet light can break it apart, splitting the water into hydrogen, which is light and escapes to space, and oxygen, which is heavier and lingers behind, building up in the air. The same ultraviolet light can crack carbon dioxide and free oxygen from it. Around certain kinds of stars, the right chemistry can fill a lifeless sky with oxygen through nothing but radiation and time. And here is the cruelest version of all. A world that is dying, a world losing its entire ocean to a runaway greenhouse, cooking its seas away into the sky, will, for a long stretch of that death, show an atmosphere flooded with oxygen, exactly as the water tears apart overhead. So the clearest sign of life we knew how to look for turns out to be, in some cases, the clearest sign that a world is in its final agony. Oxygen can mean a planet full of breath, or it can mean a planet breathing out one last time as its oceans rise into the air and are lost. From across the light years, reading only the colors of the air, we might not be able to tell those two stories apart. This is the deeper trouble, and it is worth naming plainly here in the small hours. It is not only oxygen. Very nearly every sign of life, we know how to look for every biosignature, as they are called, turns out to have a second explanation, a way for the lifeless universe to counterfeit it. There is no single gas, no one clean fingerprint that life and life alone can leave behind. And so each promising signal arrives already shadowed by its own innocent twin. Consider what once seemed the most convincing combination of all. Oxygen by itself can be faked. But what if you found oxygen together with methane? On our own world, those two gases should not be able to share the air for long. They react with one another. Left alone, they would consume each other and disappear within a few decades. So if we see them both, abundant, side by side in a distant sky, something must be replenishing them both, continuously, faster than they can cancel out, and on Earth, that something is life, the endless breathing of the living world topping up both gases at once. For a while, oxygen and methane together seemed like the dream signal, the thing geology could not counterfeit. But geology, it turns out, has tricks of its own. A great impact, a large body striking the planet, can flood an atmosphere with a temporary mix of just these gases, no life required. And certain slow reactions deep in the rock, where water works upon particular minerals in the crust, can release methane steadily, on their own, for ages, with no living thing anywhere involved. So even the dream signal, the oxygen and methane that seemed beyond faking, can be faked. The dead crust of a world can sit there, quietly breathing out the very gases we hoped only life could make. And we have, already, lived through one small rehearsal of how this will feel. Return, for a moment, to that distant world we met in the first act, K2, 18b, the possible ocean under the hydrogen sky. In the year 2023, the James Webb Telescope caught, very faintly, a hint of that molecule made on Earth almost only by life in the sea dimethyl sulfide, breathed out by drifting blooms of tiny ocean creatures. For a moment, the news traveled fast and bright. We had found, perhaps, the chemical signature of a living ocean on another world. But the signal was weak. In the careful language of the science, it sat below the threshold that physicists require before they will call a thing real. It had not crossed the line that separates a genuine detection from a trick of the noise. And the follow-up observations, gathered and argued over through the year 2025 and beyond, did not settle it. They left it hanging. We may have caught the scent of life on another world. Or we may have caught nothing but the ordinary flicker and hiss of the measurement itself, arranging itself by chance into a shape we wanted to see. And the honest, deflating truth is that we cannot yet tell the difference, and we may not be able to tell the difference for years, perhaps for decades to come. There is a still larger problem standing behind all of these, and it does not go away no matter how good our instruments become. Even with a perfect telescope, even with a flawless reading of a distant atmosphere, the biosignatures themselves will always carry this doubt, because we cannot go there. We cannot land and dig and hold a sample up to the light. We cannot run a single experiment on the thing itself. We are reading the chemistry of a world we can never touch, through a thread of light that has crossed an ocean of emptiness to reach us. And from that thread alone, we are asking the largest question there is. Is it alive? And a thread of light, however carefully read, can only ever give us a likelihood, a leaning, a probability. So when the announcement finally comes, and someday, in some form, it surely will, it will very likely not arrive as a clean and ringing yes. It will arrive as a number and a careful hedge. A 65% confidence, an 80% confidence. A statement of odds, surrounded by qualifications, defended and attacked and re-examined for years afterward, with reasonable people lined up on every side. We are trying to diagnose the presence of life across the entire width of the galaxy, with instruments designed, in truth, for somewhat different work, hoping all the while that the distant world will be generous enough to send us a sign too clear to argue with. And life, as far as we have ever seen, is rarely so cooperative as that. This, then, is the uncomfortable truth resting at the very center of this whole field of study, and it is worth saying as softly and as plainly as it can be said. We have no instrument, not one that exists today, and not one that is seriously planned, that could ever definitively confirm life on a true Earth-like world around a sun-like star. The technology, to be certain, does not exist. And even if it did, even if we built it and flew it and pointed it at the right place, we might still find ourselves looking for the wrong signals, entirely chasing the breath of a kind of life that resembles our own, and missing, completely, anything that does not. There is an equation that hangs over all of this quiet, famous, and far more honest than it is usually given credit for. It was written down in the year 1961 by an astronomer named Frank Drake, in preparation for a small meeting of people who wanted to think seriously, for the first time, about whether anyone else was out there. And it has shaped the way we have felt about that question ever since. The equation is not really a calculation, though it wears the clothes of one. It is a chain, a series of fractions and rates, multiplied one after another, each one narrowing the last. You begin with how often new stars are born. You multiply by the fraction of those stars that have planets at all. Then by the number of planets around each of those stars that could in principle support life. Then by the fraction of those suitable worlds where life actually, somewhere, manages to begin. Then by the fraction of those living worlds where life eventually grows complex enough to become intelligent. Then by the fraction of intelligent worlds that develop a technology capable of reaching out across the dark. And finally, by the length of time such a technological civilization survives before it falls silent. Multiply that whole chain together, link by link, and out the far end comes a number, an estimate of how many civilizations might, right now, be out there in our galaxy, able and willing to be heard. It is an elegant way of organizing our ignorance. And that, in the end, is mostly what it does. Because think about what was truly known in the year 1961, when Drake first wrote it down. The first term, how often stars are born, was reasonably well understood, even then. But every single term after the second was, at the time, a pure guess. Nobody knew what fraction of stars had planets. Nobody knew how many of those planets might be suitable, or how readily life begins, or how often it grows clever, or how long a clever civilization lasts before it ends. Each of those was a number pulled, more or less, out of hope and intuition, and any one of them could be wrong by a factor of millions without anyone being able to object. You could make the equation promise a galaxy crowded with company, or a galaxy utterly empty, simply by nudging the guesses, and no one could say which version was right. Drake's equation, in its first decades, was not a measurement of how many neighbors we have. It was, if we are honest, something closer to a prayer, a longing for company, written out carefully in the notation of mathematics. And here is the strange and sobering thing about where we now stand, more than 60 years later, with our 6,000 worlds and our great telescopes. We have managed, in all that time, to fill in exactly one of those terms. 1. We now know, at last, what fraction of stars have planets, and the answer, as Kepler taught us, is very nearly all of them. That term is essentially settled. We can write it down with confidence. It took us most of a century, and several spacecraft, and the careers of thousands of people to nail down a single link in the chain, and every term after it remains, even now, almost entirely unknown. Walk through what we can honestly say. The fraction of stars with planets close to 1. That one we have. The number of habitable, rocky, temperate worlds per star, here our catalogue, offers us dozens of candidates. But we have seen, all night long, that we cannot confirm a single one of them is truly Earth-like, and that the ones we can see best are the ones least likely to qualify. So that term is still, in truth, unknown. The fraction of suitable worlds where life actually begins for this, we have exactly one example, our own, where life appeared remarkably early, within perhaps the first 500 million years after the world had cooled. But is that fast or slow? Is it common or a fluke? With a single example, we cannot say. One data point draws no curve. The fraction of living worlds that grow intelligent again, we have one case, our own, and on our own world, a creature capable of building a telescope and asking these questions appeared exactly once after nearly 4 billion years of life that never did. That might mean intelligence is a near inevitable destination. Or it might mean it is a vanishingly rare accident. We have no way from a single instance to know. And the last term, the lifetime of a technological civilization, how long a species like ours lasts once it gains the power to be heard, before it falls quiet again. For this, we have no example at all that has finished. We have been capable of sending signals into the dark for only about 100 years. Whether we will go silent in the next century, by our own hand or by simple bad luck, or whether we will endure for 100,000 years more, is completely unknown to us. And that final term, the most uncertain of them all, turns out to be the one that matters most, because it alone can swing the whole answer between a galaxy briefly sparking with thousands of voices that never overlap in time, and a galaxy quietly, permanently full. So the Drake equation, rightly understood, does not tell us how many others are out there. It tells us, term by patient term, the exact shape and size of our own not knowing. It is a map of our ignorance, drawn with great care. And after 60 years of work, we have colored in one small corner of that map and left the rest of it blank. There is another branch of this search that we have not yet touched tonight, and it is worth a quiet visit before we come to the silence itself, because not everyone who looks for company out among the stars is reading the chemistry of distant air. Some, instead, have spent their lives listening not for the breath of simple life, but for the deliberate signal of something that builds and thinks and might be trying to be heard. For more than 60 years now, in scattered and often underfunded efforts, people have pointed radio telescopes at the sky and simply listened. The reasoning is gentle and hopeful. A living world, breathing oxygen into its air, betrays itself only by accident, through chemistry, in a signal so faint we can barely catch it across a few light years. But a civilization with technology might betray itself on purpose, or at least far more loudly through the radio chatter that leaks from a busy world, or through a beacon deliberately aimed outward, a steady tone laid down on a single clean frequency, the kind of signal nature does not easily make on its own. Such a signal could cross enormous distances and still be recognizable as the work of a mind. And so, for decades, we have swept the heavens, channel by channel, star by star, waiting for one clear note to rise up out of the natural hiss and crackle of the universe. The listening has, on the whole, returned the same answer as the looking: quiet. In all those years of sweeping the sky, there has been just one famous moment that has never been fully explained, a single, strong, narrow burst of radio noise picked up one night by a telescope long ago, lasting a little over a minute and then gone, never to repeat, despite every effort since to catch it again. It may have been something natural that we simply did not understand. It may have been some passing interference from our own world, reflected or confused. It was almost certainly not a message, but it has lingered in the imagination for half a century, precisely because it was the one time the universe seemed, for 72 seconds, as though it might have been about to speak and then said nothing more. There are stranger things people have learned to look for too. If a civilization grew vast enough and hungry enough for energy, it might begin to build on a scale we could actually notice from afar, great structures gathered around a star to catch its light, so many of them that the star itself would dim and redden in a way no natural star quite does, glowing with waste heat in the infrared. We have searched here and there for stars behaving in just that odd way. Now and then one turns up that flickers strangely, and for a little while people wonder. And then, each time so far, a quieter natural explanation arrives. A cloud of dust, a swarm of comets, an ordinary thing wearing an extraordinary disguise. The great structures, if they exist anywhere, have not yet shown themselves to us. The stars, when we look closely, keep turning out to be only stars. So both branches of the search, the looking and the listening, the breath and the beacon, have led us to the same wide quiet. We have read the air of distant worlds and found no certain life. We have swept the sky for signals and heard no certain voice. Two entirely different methods, two entirely different hopes, and the same patient silence waiting at the end of each. Which brings us, gently, to the oldest and largest question of all, the one that has been waiting underneath this whole night, and that we can no longer quite avoid, which brings us, at the very last, to the quietest fact of all, the one that waits underneath every other thing we have spoken of tonight. It is sometimes called the Fermi paradox, after the physicist who is said to have posed it over lunch one day, almost casually, as a simple question that has never since stopped echoing. Let us state it as plainly and gently as it can be stated. Our galaxy holds somewhere between 100 and 400 billion stars. We now believe it holds, at the least, 300 million potentially habitable worlds. And it is old. The galaxy has been turning for something like 13.5 billion years, time almost beyond comprehension, far longer than our own star has even existed. In all that vastness and all that time, even a single civilization with only modest patience and modest technology, spreading slowly from star to nearby star, could have crossed the entire galaxy from end to end in something like 10 million years. And 10 million years, against the age of the galaxy, is the smallest sliver, a single afternoon in a very long life. There has been time, many times over, for the galaxy to have been filled. And yet, when we look and when we listen, silence, no signals threading through the noise, no structures glinting around distant stars, no ships, no probes, no messages, no unmistakable mark of anyone having ever passed this way. Nothing. We have not searched every corner, and we have not listened on every frequency, and the silence is not yet proof of anything, but it is loud in its own way. The night sky, for all its hundreds of billions of stars, has so far answered our every question with the same vast and patient quiet. There are many ways to make peace with that silence, and we will sit with just two of them, gently as the night closes in. The first is the possibility that Earth is genuinely, deeply rare. We have spent this whole night cataloging how many things a world seems to need before it can hold complex life, the right kind of star, calm and steady and long-lived, the right place in its system, an atmosphere of the right thickness, a magnetic shield, a steadying moon, a distant giant to guard the inner worlds, a slowly breathing crust, a stable climate held together across billions of years. Each of those on its own may be uncommon, and to get them all at once, in one place, may be so unlikely that it happens only a handful of times in an entire galaxy, or perhaps only once. If that is true, then a second Earth might indeed exist somewhere, and yet be so rare that we are searching for it across 300 million candidate worlds, most of which we cannot even see clearly, with instruments that could not confirm it if they found it. We might be looking, in other words, for the only other one. A single distant twin lost somewhere in an ocean of almost Earths. And the second way of making peace with the silence is stranger and quieter, and it carries a thought at the bottom of it that is worth holding very carefully because it turns our entire search gently on its head. Imagine that there is some great barrier in the long road from lifeless rock to lasting, star-faring civilization, some step somewhere along the way that almost nothing ever gets past. A filter. It might lie behind us. Perhaps the very beginning of life is the hard part, or the leap to complex cells, or the rise of intelligence. And we have already, improbably, come through it, which would mean the road ahead is open. Or the filter might lie ahead of us still. Perhaps civilizations like ours reliably destroy themselves or stall or fall silent soon after they gain the power to be heard. And that is why the sky stays quiet. We do not know which it is. And here is the gentle, upside-down conclusion that some have drawn from it. If the great filter lies ahead of us rather than behind, then finding a second Earth, and worse, finding a dead one, a world bearing the faint chemical traces of a life that once thrived and then ended, with no voice left and no signal and no sign of anyone still there, would not be a comfort at all. It would be the most quietly frightening thing we could possibly discover. It would suggest that the silence is not because life is rare, but because life is fragile, that the road runs out again and again, somewhere up ahead, and that we are still walking toward whatever waits at the end of it. There is a third way to sit with the silence, gentler than the other two, and it has been quietly gaining favor among the people who think hardest about these things. It does not require that Earth be vanishingly rare. It does not require that some terrible filter lie waiting ahead of us. It requires only that we look honestly at the clock of the universe and notice where on that clock we happen to be standing. We tend to think of the universe as old, and in the only terms we have, it is something close to 14 billion years have passed since the beginning, a stretch of time so far beyond a human life that the mind simply slides off it. But here is the thing that almost no one mentions because it runs so strongly against the feeling of lateness, of having arrived at the end of a long story. In cosmic terms, the universe is not old at all. It is young. It is barely past its dawn, and the overwhelming majority of all the time there will ever be still lies ahead of it, unspent. Consider the stars, the great bright stars, the ones that blaze and die quickly, are the rare and showy exceptions. The most common stars by far, as we have seen all night, are the little red dwarfs, and a red dwarf does not burn for billions of years, as our own star will. It burns for trillions. Some of them will go on glowing slowly and frugally and steadily for 10 trillion years or more, which is to say, for something like 1,000 times longer than the entire age of the universe so far. The little red stars now scattered across the sky have barely begun their lives. They have an almost unimaginable stretch of quiet burning still ahead of them. And new stars are still being born all the time out of the gas and dust between the others, and will keep being born for 100 trillion years to come, long after our own sun has cooled to a dark ember and been forgotten. So lay out the whole timeline, the real one, end to end, the full span over which the universe will be capable of making warm, lit, life-bearing worlds. Against that vast future, the 14 billion years that have passed so far are not the body of the story. They are the first faint sentence of it. We are not living near the end of the age of life in the cosmos. We are living at the very beginning of it, in the first thin sliver of the first chapter, when the ink is barely dry on the page. And if that is true, then the silence takes on a wholly different and far kinder meaning. Imagine arriving at a great hall very early, before almost anyone else has come. The lights are on, the tables are set, everything is ready and waiting. But the room is nearly empty, because you are among the first to arrive, and the others, most of them, have not been born yet and will not arrive for a very long time. You could stand in that quiet hall and conclude, sadly, that no one is coming. Or you could understand that you are simply early, that the quiet is not the quiet of an empty universe, but the quiet of a universe that has only just opened its doors with the whole long evening still ahead of it. We may be early. We may be among the first minds anywhere to wake up and look around and start asking the question at all, not because life is doomed and not because Earth is a freak, but simply because there has not yet been enough time for the slow trillion-year stars to bring forth whatever they are going to bring forth in their own unhurried way. The company we are looking for may not be absent. It may be still to come. We may be the early ones, the first faint candle lit in a hall that will, over ages we cannot picture, slowly fill with light. There is a strange dignity in that thought, if it is true. It would make us not the lonely survivors of a galaxy that failed, but the first arrivals in one that is only beginning. It would mean that the silence we hear is not an answer at all, but a kind of waiting the long, patient pause before a story that has scarcely started. And it would mean that the work we do now, the looking and the listening and the careful building of instruments, is not the desperate searching of a species afraid it is alone, but the first tentative steps of a very early guest, learning the shape of a room that the rest of the evening's company has not yet entered. And so, holding all three of these gently at once, that Earth may be rare, that the filter may lie behind us, that we may simply be early. We arrive at the soft and surprising thought that has been waiting at the bottom of this whole search all along. The best possible result of all our looking, the most hopeful thing the universe could tell us might, just might, be to find nothing. To search the 300 million worlds and the thousands of almost Earths, and to hear only the patient quiet, and to conclude that the hard step lies safely behind us, already past, and that the long road ahead might yet be ours to walk. The empty sky, in that strange light, is not loneliness, it is permission. It would be easy to end on the silence and on the long odds, and to let the whole thing settle into a kind of beautiful despair. But that would not be quite honest, because it would leave out the part of the story that is still being written, the part where, despite everything we have laid out tonight, people are quietly building the machines that might one day push past every wall we have described. So, before we let the night close fully in, let us spend a little while with the future, gently, and with what it might take to get there. Start with how recently all of this began. It is worth remembering that the very first planet ever confirmed around an ordinary star like our own was found only in the year 1995, a strange, hot, swollen giant whipping around its star every 4 days, a world nobody had predicted and nobody quite believed at first. That was within living memory. A person not yet old can remember a time when we knew of no other worlds at all, anywhere, and had no proof they existed. Everything we have spoken of tonight, the 6,000 worlds, the catalogue, the almost Earths, the whole science of reading distant atmospheres, all of it has grown up in the space of a single human generation. We are not at the end of this search. We are very near the beginning of it. We are the people who happen to be alive for the first chapter. And the tools have been multiplying. After Kepler finished its long stare, a successor went up in the year 2018, a telescope that, instead of fixing its gaze on one distant patch of sky, sweeps slowly across nearly the entire sky, watching the nearest and brightest stars for those same faint transit shadows. The thinking behind it was simple and wise. Kepler proved that planets are everywhere by staring deep at faraway stars. Its successor would find the planets close enough and around stars bright enough that we might actually be able to study them in detail afterward. It has turned up thousands of new candidates, many of them circling stars near enough to be followed up by the great atmosphere-reading telescopes. It is, in a sense, a scout going ahead, mapping the nearby ground, marking the worlds worth a closer look. Then there is the James Webb Telescope itself, which we have already met, and which is even now, night after night, doing the patient work of reading the skies of distant worlds, one slow transit at a time. We have seen its limits, that for a true Earth around a true sun, it is very nearly, but not quite, powerful enough. And yet for the larger worlds, and for some of the planets around those small red stars, it is rewriting the textbook in real time, finding the gases in alien air, testing whether the worlds around red dwarfs have managed to hold on to any atmosphere at all. Every one of those readings, even the disappointing ones, even the ones that come back showing a bare and airless rock, is a real answer. Where before there was only a guess, the catalogue of our ignorance is slowly being filled in. And out beyond these, on the horizon, are the instruments still being built and still being dreamed. There is a telescope named for Nancy Grace Roman, expected to fly soon, carrying with it a new kind of starlight blocking mask, a tool meant to prove that we can photograph planets directly, blotting out the star to catch the faint companion beside it. It will manage this first for the large worlds, the Jupiters, far from their stars. But it is a rehearsal. It is the first real test of a technique that, refined and enlarged, might one day be turned on a true Earth. On the ground, meanwhile, a new generation of enormous telescopes is rising mirrors not a few meters across, but 30, nearly 40 meters wide, built in segments and assembled on remote mountaintops under the clearest skies on Earth. With light gathering power beyond anything we have ever had, they may be able to tease the faint glow of a small rocky world out from beside its star, and even to begin reading the colors of its air from the surface of our own planet. And then there is the instrument that does not yet exist, but that the people who think carefully about these things have been quietly designing on paper for years, a great space telescope built for one purpose above all others: not to find more hot giants, not to read the skies of mini Neptunes, but to do the single hardest thing in all of this: to take the direct image of a true Earth-sized world in the habitable zone around a calm and ordinary sun-like star, and to spread its faint, reflected light into a spectrum, and to read its atmosphere for the gases that might, just might, mean life. Such a telescope would need to block out the glare of a star 10 billion times brighter than its target, perhaps with a mask inside the telescope, perhaps with a vast, precisely shaped screen flown separately tens of thousands of kilometers ahead of it, unfurling like a great dark flower to cast the telescope into the star's shadow, so the planet beside it might be glimpsed. The engineering is at the very edge of what we can imagine doing, and the goal is nothing less than to look upon a few dozen of the nearest potentially habitable worlds one by one, and to ask each of them directly the question we have never yet been able to ask: are you alive? It will not come soon. The honest timelines for such a thing reach out into the decades ahead, into years that some of the people who will finish it have not yet been born to see. And there is something fitting in that, something that returns us to where this all began. The search for a second Earth was always going to be longer than any single life. It is the kind of work a civilization does slowly, across generations, each one inheriting the instruments and the questions of the last, refining them a little, handing them forward a little improved. The person who finally reads the air of a living world and knows it for what it is may be the great-grandchild of someone alive tonight. They will stand on everything we are building now, the way we stand on the work of the people who, 30 years ago, did not even know for certain that other worlds were real. So the silence is not the end of the story. It is only as far as we have managed to get, so far, this early in the looking, with the first few instruments we have learned to build. The machines that might break the silence are being sketched and funded and argued over and slowly made real, right now, by people who have made their peace with not seeing the finish. And that, too, is part of what it means to look to keep building toward an answer you may never personally receive, simply because the question is worth it, and because someone, someday, should get to know. Before we let the night fully settle, let us walk back, slowly and without hurry, through the worlds we have met, not to study them again, but simply to visit them once more, the way you might wander through the rooms of a house at the end of a long day, turning off the lights one by one. There was Kepler 22b, the first of the almost Earths, 620 light-years off the one the headlines called a twin. Before we understood that at 2.5 times our width it was very likely a world of swollen gas or an ocean without any shore. Picture it out there still, turning patiently in the dark, exactly as indifferent to our hopes as it has always been. It does not know it was ever called a twin. It simply goes on, around its star, as it has for billions of years and will for billions more. There was Proxima b, the nearest of all, only 4 light-years away, around the small red ember that is our closest stellar neighbor, Earth-sized, in the warm band, and almost certainly scoured down to bare stone by a star that erupts in flares far fiercer against its dim red glow than our own ever does. So close in the scheme of the galaxy, and still so far beyond any reach we have, or are likely to have, for a very long time to come. There were the 7 worlds of TRAPPIST-1, the little nested system, 3 of them in the gentle band. All of them most likely locked in place, one face to the fire and one to the frost, with a thin ring of twilight strung between, where the winds may run faster than sound. 7 Earths around one star, and not a single safe place among them. And yet what a thing, simply to know they are there. 7 worlds, where 2 human lifetimes ago we knew of none. There was K2-18b, the world under the hydrogen sky, where we caught the faintest possible whisper of a molecule that, on our own world, only life knows how to make a whisper too soft to trust, hanging unresolved, neither confirmed nor dismissed, waiting for instruments we have not yet built. And there was the ice twin, found in our own recent months, only 6% wider than our world, around a calm and ordinary star at last, and riding too far out, perhaps wrapped forever in a shroud of frost. Each of them an almost. Each of them a near miss, a not quite. A world that satisfied one requirement and quietly failed the rest. And each of them, in its own way, a small miracle simply to have found at all, a point of light resolved into a place, a shadow resolved into a world, by people patient enough to watch and wait. And notice, if you have not already, how strange and plain their names are. Kepler 22b, Proxima b, TRAPPIST-1f, and G and HK 218b, L98-59f. They are not names, really, so much as catalogue entries the letter and number of a filing system, the address of a thing in a database. There has been no time, and no reason yet, to name these worlds the way we once named the planets of our own family, after the old gods, with all the weight of story behind them. They are too many, and too far, and too newly found. And yet each of those dry little labels marks a real place, a genuine world with a genuine surface or a genuine sky, turning in genuine light, as solid and as actual as the ground beneath you, whether or not any eye will ever look upon it. Somewhere out there, right now, the place we have filed under K218b is having its weather. The world we call Proxima b is turning its one scorched face toward its small red star, as it has for billions of years, under a name that means nothing to it. There is something quieting in that the universe is full of real places that we have only just begun to find and have not yet had the time to love enough to name. It is worth pausing, here in the quiet, to think about those people, because behind every world we have named tonight, behind every faint dip in starlight and every gentle wobble measured down to the pace of an idle step, there are human beings who gave years of their lives to the catching of it. This is not fast work. It is not the work of sudden flashes and shouted discoveries, whatever the headlines later make of it. It is the work of staring, of building an instrument over a decade and calibrating it for another year, and then gathering observation after observation after observation, hundreds of them, night upon night, season upon season, most of them showing nothing at all. It is the work of subtracting noise, and arguing over thresholds, and waiting for a third transit to confirm what 2 transits hinted at, which can mean waiting 3 more years simply to be sure of a single world. It is, in its texture, one of the most patient things our species does. The people who find planets are, by temperament and by training, people who have made peace with waiting, who can hold a question gently in their minds for the length of a career and not need it answered tomorrow. And there is something quietly moving in that, when you sit with it. We are a restless species mostly. We want answers quickly and we grow bored and we move on. And yet, scattered across the world, there are people who have chosen to spend their one short life leaning over the faint light of stars that will not change in any way they will ever live to see, asking the largest and oldest question there is, knowing they will very likely die before it is answered. They do it anyway. They add their single small term to the great equation of our ignorance, and they hand the rest forward to whoever comes next. The search for a second Earth is, in the end, a relay run by people who will never see the finish line and who run their leg of it carefully all the same. Let us widen out now, and let the scale of the thing grow large around us, the way the dark grows large when you lie still in it long enough. Our galaxy has been turning for something like 13.5 billion years. Our own star is younger than that, about 4.5 billion years old, a little under halfway through its long, steady life. Life appeared on our world remarkably early, within perhaps the first 500 million years after the surface had cooled and the oceans had gathered. And then, for the longest stretch of the story, it stayed simple. For billions of years, there was nothing on Earth but the smallest living things, drifting and dividing in the sea, with no eyes to see the sky and no minds to wonder about it. Complex life, large life, life you could have watched moving, came only in the last several 100 million years. And a creature that could build a telescope and turn it outward and ask whether anyone else was out there, that came only in the last few thousand. The blink of an eye, laid against the age of the world, the smallest mark at the very end of an immensely long line. And our ability to send any signal at all out into the dark to be heard, even in principle, across the gulf between stars, is younger still. About 100 years old, a single human lifetime. Against the 13.5 billion years the galaxy has been turning, 100 years is so small it very nearly does not exist. If the whole age of the galaxy were compressed into a single year, our entire history of listening to the sky would occupy the last fraction of the last second before midnight. We have been awake and paying attention for almost no time at all. There is a strange comfort tucked inside that smallness, if you let yourself feel it. It means that the silence we have heard so far proves very little. We have barely opened our eyes. We have listened, in a focused way, to a tiny handful of stars on a narrow range of frequencies, for the briefest sliver of time. To conclude from that the galaxy is empty would be like dipping a single cup into the sea, finding it holds no fish, and deciding the ocean is lifeless. The quiet we have heard is not yet an answer. It is mostly a measure of how little we have so far had the chance to ask. Let us imagine for a little while the day it finally happens, not because we can know that it will, but because it is a gentle thing to picture, and because picturing it tells us something about the search itself. It will probably not arrive the way the films have taught us to expect. There will most likely be no single shattering moment, no light in the sky, no voice breaking through on every screen at once. What there will be, instead, is a paper. A quiet, careful, heavily checked piece of work, published one ordinary week, describing a particular distant world and a particular set of gases found in its air, and a particular estimate of how likely it is that those gases were made by something alive. And the estimate will not say yes. It will say something far more cautious and far more human than that. It will say that the chance is high, perhaps very high, but not certain. It will be surrounded by qualifications, by alternative explanations not yet fully ruled out, by calls for more observation, by the patient hedging that careful people use when the stakes are large and the evidence is faint. And then, instead of an answer, there will be an argument, a long, slow, civil, necessary argument carried out over years as other groups turn their own instruments toward the same world and check and recheck and propose other ways the signal might have come about without any life at all. Some will be convinced, some will not. The confidence will creep upward, observation by observation, the way the certainty about any real thing in science creeps upward, never in a single leap, but in a long accumulation of careful work, until one day people look up and realize that, somewhere along the way, almost without anyone announcing it, the thing became true. That is how the largest discovery in human history will most likely feel. If it comes, not like a thunderclap, like a slow sunrise, where you cannot name the exact moment the dark became light, only that, at some point, it had. And here is the strange and quiet thing about that day, whenever it comes. It will change everything, and it will change almost nothing. Everything. Because we will know, at last, that we are not alone in the simplest and deepest sense that life is something the universe does more than once, given a gentle enough place and enough time, and that the long silence was never quite as total as it seemed. The story we tell about ourselves, about why we are here, and whether it means anything, will never again be told in quite the same way. And yet, almost nothing, because the next morning the world will still turn, and the kettle will still boil, and the small, ordinary business of being alive will go on exactly as before. The distant world will be no closer than it was. We will not be able to visit it, or speak to it, or learn anything more about it than the thin thread of its light allows. It will simply hang there, as it always has, around its star, indifferent to having been found. And we will go on, carrying the new knowledge gently, the way you carry any large thing, getting slowly used to its weight. There is a kind of peace in understanding this in advance. It means we do not have to wait, anxiously, for a moment that may never come in the sharp form we imagine. The search is not a held breath waiting to be released. It is a long, slow exhale already underway that will go on long after us. Whatever the answer turns out to be a galaxy quietly full, or a galaxy almost entirely empty. With us, the rare and lucky exception, it will arrive softly, in pieces, over years and lifetimes, and there will be time enough to take it in. You do not have to be ready for it tonight. No one does. It is not that kind of question, and this was never that kind of search. It is worth asking, softly, somewhere near the end of all this, why do we do it? Why spend the careers, and the patience, and the great sums, and the staring on a question we may never answer, for a twin world we may never find, and could not reach, even if we found it? Part of the answer is simple curiosity. The oldest engine we have, the same pull that made the first people lie back on a hillside and wonder what the lights were. But there is something gentler underneath the curiosity, and it has to do with the strange loneliness of being the only voice you have ever heard. For the whole of our history, we have looked out at a sky full of fire and found no answer in it. Every story we have ever told about the heavens, we told to ourselves. And so the search for a second Earth is, in part, a search for an end to that solitude, a hope that somewhere around one of those countless patient stars, there is someone or something looking back, asking the same question into the same dark, perhaps even wondering about us. To find another living world would be to learn that life is not a single accident that happened once and need never have happened at all, but a thing the universe does, given time and a gentle enough place to do it. That alone would change how it feels to be here. And part of the answer is that the looking teaches us about home, whether or not it ever finds another. Every almost Earth that fails, every world too hot, too cold, too locked, too flared, too swollen, too bare, quietly teaches us how much had to go right here, for us. We did not understand how unusual a steady star might be until we met the temperamental ones. We did not understand the gift of a thick and lasting atmosphere until we watched, in our models, how easily such an atmosphere can be stripped away. We did not understand the quiet, ceaseless work our own world does, the breathing crust, the steadying moon, the magnetic shield, the gentle and reliable seasons until we went looking for it elsewhere, again and again, and so rarely found it. The search for a second Earth has turned out, in practice, to be one of the great teachers of the value of the first. So consider, for a moment, before you drift off, the world you are lying on right now. It has a star that is calm, not a small red ember that erupts without warning and tears at the sky above it, but a steady, patient, middle-aged sun that has poured out very nearly the same gentle warmth morning after morning for billions of years, and will go on giving it for billions more. And the world sits at just the right distance from that warmth, not so near that the seas boil away, as on Venus, and not so far that they lock into ice, as on Mars, but in the narrow place between, where water has lain in deep and open oceans across the entire long history of life. Think of what that distance alone has brought: rain and rivers and tides, and the simple fact of being able to cup cool water in your two hands. And the world turns, evenly and unhurried, so that no face is held forever to the fire and none forever to the frost, so that there is morning and noon and evening, and the soft daily passage from light into dark and back again, that every living thing here, you included, has been built around. And all the quieter machinery is here too, working without pause and without notice. A moon, large and close, steadying the lean of the world so the seasons return in their reliable order rather than tumbling into chaos. An iron heart turning deep below, throwing out an invisible shield that turns aside the worst of what the star breathes outward so the air is not stripped slowly away into space. A living crust that breathes the climate steady across the ages, drawing down warmth when the world runs hot and giving it back when the world runs cold. A distant giant standing guard far out beyond, catching much of the falling debris before it can ever reach us. You have felt none of this happening, and you never will. And yet every one of these, each of them absent, somewhere, on one almost Earth or another, is present here, all at once. By some long chain of fortune we are still only beginning to understand, holding quietly together beneath you while you rest. We have spent the whole of this night looking outward, into the dark, at the almost Earths and the locked worlds and the flaring stars and the silence between them. And the quiet lesson, folded up inside all of it, is that the most remarkable world in the entire catalogue, the only one we have ever confirmed to hold a single living thing, the only one where the question itself could even be asked, is the one you are resting on at this very moment. The rare one, the improbable one, the one that got everything right. Not a second Earth, somewhere far away. The first one, this one, home. It is a curious thing to go searching the whole galaxy for a world like your own, and to find, after 30 years and 6,000 tries, that the best example of it is the one you set out from. Every failed candidate is a small note of gratitude in disguise. Every locked and flaring and frozen and airless world we cross off the list is the universe quietly reminding us how much had to align here, and how gently, for there to be a soft place to lie down at the end of a long day, under a calm sun, on solid ground, beneath a breathable sky, and simply rest. We went looking for a twin, and what we keep finding, over and over, in the shape of its absence, is the quiet worth of home. So let the search go on out there in the dark, slow and patient as it has always been. Let the telescopes keep their vigil over the distant stars, catching the faint shadows of worlds, weighing them by the gentlest of tugs, reading the colors of skies we will never stand beneath. Let the people who do this work keep their long and faithful watch, adding their small certain terms one at a time to the great unfinished equation and handing the rest forward to whoever comes next. There is no hurry. There has never been any hurry. The stars will keep, the worlds will keep, the question will keep, and you do not need to hold any of it tonight. You do not need to solve the silence, or find the twin, or settle whether the filter lies ahead of us or behind. You do not need to decide whether the empty sky is loneliness or permission. Those are questions for the morning, and for other people, and for years and lifetimes still to come. They will still be there, patient and unhurried, long after you have closed your eyes. For now, there is only this: a calm star warming a rare and quiet world, a thin sky and a steady turning, and a soft daily passage from light into dark. 6,000 distant worlds turning faithfully around their stars, asking nothing of you. And the gentle, ordinary, improbable fact of being here at all, on the one world in all the catalogue where it was ever possible to lie still in the dark and wonder and rest. Let the number go. 6,000 worlds, 300 million more unseen. Let them drift out past the edge of your thoughts, the way the lights of distant houses drift past a train window in the night, there and then gone, no longer anything you need to watch. Let the catalogue close, let the silence be, for now, only silence soft and wide and untroubled. And let yourself gently, here on the rarest world we have ever found, drift the rest of the way down into sleep.